When temperatures hit -96 degrees Fahrenheit in Oymyakon, when blizzards rage for days across the Sakha Republic, survival depends on building a shelter that transforms the world's most brutal winter into a livable space. The Yakuts thrived in the coldest permanently inhabited place on Earth for over 1,000 years, using construction techniques so sophisticated that modern thermodynamic studies are still uncovering their secrets. In 1933, Oymyakon recorded -96.16 degrees Fahrenheit, yet Yakut families lived through that winter in shelters maintaining 55 degrees Fahrenheit inside, using only wood, clay, and refined engineering knowledge. During WWII, these designs saved thousands of deported Lithuanians, Latvians, and Finns. The grateful Lithuanians later built a memorial balaghan near Kaunas, testament to Yakut architectural wisdom. The balaghan creates a thermal microenvironment that sustains life when the outside world becomes uninhabitable. Modern survival schools charge thousands for techniques that pale compared to what Yakut families built with hand tools. Here's exactly how they did it, step by step. Tools to trust. Skills that last. This is Bushcraft Arsenal. Step 1. Foundation and permafrost. Management building on permafrost requires understanding that the ground beneath your feet is harder than concrete and will remain frozen year-round, but any heat from your shelter will cause catastrophic thaw that can destroy the entire structure. The Yakuts developed a foundation system that works with the permafrost rather than against it, creating a stable base that has supported structures for centuries. The foundation begins with selecting a site where the permafrost layer is stable and deep, typically on slightly elevated ground where drainage prevents water accumulation that could create unstable ice lenses. Yakut builders would test the permafrost by driving wooden stakes into the ground during the warmest part of summer. If the stakes couldn't penetrate more than a few inches, the permafrost was solid enough for construction. 4 vertical corner posts form the primary foundation, each buried 3 to 4 feet into the permafrost using techniques that prevent thermal bridging. The posts are positioned using a traditional measuring system based on the builder's body proportions, ensuring the structure fits the intended occupants perfectly. These aren't simple posts. They're carefully selected logs, typically larch or birch, seasoned for at least 2 years to prevent warping and cracking in extreme cold. The critical innovation lies in how these posts connect to the permafrost. Rather than simply burying them, Yakut builders create a thermal break using layers of birch bark and dried moss that prevent heat conduction from the structure into the permafrost. This insulation system allows the shelter to maintain interior warmth without destabilizing the foundation, a principle that modern permafrost construction still follows today. Between the corner posts, intermediate supports are placed every 6 feet for larger structures, creating a framework capable of supporting massive snow loads that can exceed 2,000 pounds per square foot during severe blizzards. Each support post is notched at the top to receive horizontal beams, with the notches cut at precise angles that distribute weight evenly and prevent splitting under load. Drainage channels around the perimeter direct meltwater away during summer thaws, preventing ice dams that could destabilize the foundation. Step 2. Structural framework and load distribution. The balaghan's framework represents centuries of engineering refinement, creating a structure that can withstand blizzard winds exceeding 100 miles per hour while supporting snow loads that would collapse conventional buildings. The framework uses a sophisticated system of interlocking beams and supports that distribute forces throughout the entire structure rather than concentrating stress at individual points. Horizontal beams rest on the notched tops of the vertical posts, forming the primary load-bearing framework. These beams are typically 8 to 12 inches in diameter and up to 20 feet long, selected from the straightest, strongest trees available. The beams are connected using traditional joinery techniques that create joints stronger than the wood itself. No nails or metal fasteners that could fail in extreme cold. The central ridge beam can reach 16 inches in diameter and serves as the backbone of the entire roof system. This massive timber is positioned using a complex system of ropes and levers, requiring the coordinated effort of multiple families during construction. The ridge beam's size isn't just for strength. Its thermal mass helps stabilize interior temperatures by absorbing and releasing heat slowly throughout the day-night cycle. Supporting the ridge beam are curved wooden blocks, some weighing over 200 pounds, that create the balaghan's distinctive domed roof profile. These blocks aren't randomly shaped. They're carved to specific curves that optimize snow shedding while creating maximum interior volume. The curved profile also provides superior wind resistance, allowing blizzard winds to flow over the structure rather than creating destructive pressure differentials. The roof framework uses thin logs, typically 4 to 6 inches in diameter, laid perpendicular to the ridge beam and secured with shallow grooves that prevent shifting during windstorms. These logs are spaced precisely to support the insulation layers while allowing for thermal expansion and contraction that can exceed 2 inches during extreme temperature swings. Wall framing employs a unique angled construction where logs lean inward at approximately 15 degrees, creating a structure that becomes stronger under load rather than weaker. This inward lean serves multiple purposes. It sheds snow more effectively, creates better thermal efficiency by reducing surface area exposed to wind, and provides superior structural stability during ground movement caused by permafrost shifts. Corner construction uses progressively shorter logs with pointed tops fitted together using stepped notches that create weatherproof joints without gaps. These corners are the most vulnerable points in any structure, but the Yakut system creates corners that actually strengthen the entire building while providing superior insulation at these critical thermal bridge points. Step 3. Thermal insulation system and weatherproofing. The balaghan's insulation system achieves thermal performance that rivals modern construction using only natural materials available in the Siberian taiga. The system works on multiple principles: air trapping, thermal mass, vapor management, and wind resistance, all integrated into a single weatherproofing system that has kept families alive through temperatures that would kill unprotected humans in minutes. The primary insulation material is a carefully formulated mixture of clay, dried cow dung, chopped straw, and sometimes animal hair that creates a coating 4 to 6 inches thick over the entire structure. This isn't simply mud daubed on walls. It's a sophisticated composite material refined with millennial precision. These compounds weren't improvised, but precise formulations developed over centuries. Clay provides weather resistance and structural integrity, selected and tested using traditional methods that identify the ideal properties for extreme cold flexibility. Dried cow dung serves multiple functions. Its fibrous content creates insulating air pockets, while natural oils provide water resistance. The organic matter even generates small amounts of heat as it decomposes slowly throughout winter. Chopped straw creates the structural matrix that holds everything together while providing additional air-trapping capability. The straw is cut to specific lengths that optimize structural integrity without creating weak separation points. The insulation mixture is applied in multiple layers, each allowed to partially dry before the next application. The first layer, applied directly to the wooden framework, is mixed thinner to penetrate into the wood grain and create a strong mechanical bond. Subsequent layers are progressively thicker, with the final layer mixed to provide maximum weather resistance. Application requires specific weather conditions for optimal curing, with experienced builders timing the work by observing wind patterns and temperature trends. The finished insulation system creates an envelope that maintains interior temperatures 150 degrees and warmer than outside conditions. Modern thermal imaging studies of reconstructed balaghans show virtually no heat loss through the walls, with thermal bridging eliminated through careful attention to construction details that prevent direct conductive paths from interior to exterior. Step 4. Advanced heating system and sacred fire management. The heating system represents the technological and spiritual heart of the balaghan, combining sophisticated combustion engineering with sacred fire traditions that have sustained Yakut families for over a millennium. This isn't simply a fireplace, it's a precisely engineered thermal management system that can maintain livable temperatures using minimal fuel while serving as the spiritual center of family life. The stove's positioning follows strict traditional rules based on both thermal efficiency and spiritual significance. Located in the northeast corner of the balaghan, the stove's opening faces southwest, creating optimal heat distribution while aligning with traditional beliefs about fire spirits and family protection. This positioning also takes advantage of prevailing wind patterns to enhance draft and combustion efficiency. Two primary construction methods exist, each suited to different conditions and builder skill levels. The clay-coated stove represents the simpler construction method using wooden planks arranged in a slightly inclined position and coated with thick clay layers. The planks extend approximately 3 feet above the roofline, creating a chimney system that provides excellent draft while preventing downdrafts during blizzards. The more sophisticated clay-built stove begins with a wooden foundation box filled with tightly packed clay. This foundation serves as both the combustion chamber base and a thermal mass that stores and releases heat throughout the day-night cycle. The foundation box is typically 4 feet long, 3 feet wide, and 18 inches deep, sized to provide optimal thermal mass for the structure's volume. Construction of the clay-built stove requires precise timing and technique. 2 L-shaped wooden supports create the framework for the combustion chamber, with their curved ends connected to form the firebox opening. Vertical planks inserted into grooves in these supports form the chimney walls, extending 3 feet above the roofline to ensure proper draft in all weather conditions. The clay filling process represents the most critical phase of construction. The framework is temporarily sealed with boards, then filled with clay mixed to specific consistency, wet enough to pack tightly, but dry enough to maintain structural integrity. The clay is tamped in layers, with each layer compressed to eliminate air pockets that could cause cracking or structural failure. A hollow log is inserted into the clay-filled chimney during construction, creating the smoke passage when the log burns out during the first firing. This technique ensures a smooth, properly sized flue that provides optimal draft while preventing the structural cracking that would occur if the passage were carved after the clay hardened. The combustion chamber is carved from the hardened clay using traditional tools, creating an oval chamber that optimizes combustion efficiency and heat output. The chamber's shape and size are calculated based on the balaghan's interior volume, ensuring complete combustion of fuel while maximizing heat transfer to the living space. The heating system maintains 55 degrees Fahrenheit in -60 degrees Fahrenheit conditions, using only 20-30 pounds of wood daily, achieving over 80% thermal efficiency comparable to modern high-efficiency stoves. Step 5. Window systems and light management. The balaghan's window system solves the seemingly impossible challenge of providing natural light while maintaining thermal integrity in conditions where conventional windows would be useless or deadly. The Yakut solution uses materials and techniques that create functional windows capable of withstanding temperature differentials exceeding 150 degrees Fahrenheit while providing essential daylight during the polar winter. Winter windows use carefully prepared ice panels that provide both light transmission and superior insulation compared to any glass available during the balaghan's development period. The ice isn't simply frozen water. It's specially prepared using techniques that create clear, strong panels capable of lasting entire winter seasons without replacement. The ice preparation process begins in early winter, when temperatures first drop below -20 degrees Fahrenheit. Water is collected from specific sources, typically from flowing streams where the water has low mineral content that would create cloudy ice. The water is allowed to freeze slowly in shallow wooden forms, creating panels 2 to 3 inches thick with optical clarity approaching that of glass. Slow freezing creates strong, clear ice by allowing dissolved gases to escape, while rapid freezing traps air bubbles that cause cracking. Ice panels are cut to fit precisely into window openings using traditional tools, with edges shaped to create weatherproof seals against the wooden window frames. The panels are typically 18 to 24 inches square, sized to provide adequate light while remaining manageable for installation and replacement. Multiple panels can be used for larger windows, with overlapping joints sealed using snow that freezes into permanent weatherproof connections. Summer windows use bull bladder membranes that provide light transmission while maintaining weather resistance during the brief warm season. The bladders are carefully prepared using traditional techniques that create tough, translucent membranes capable of withstanding wind and weather while allowing natural light to enter the living space. Bladder preparation begins with careful selection of materials from healthy animals, typically cattle or horses. The bladders are cleaned using traditional methods that remove all organic matter while preserving the membrane's strength and flexibility. The cleaning process uses specific plant-based solutions that prevent decay while maintaining the material's optical properties. The prepared bladders are stretched and dried using techniques that create uniform thickness and maximum light transmission. The stretching process requires careful attention to tension and drying conditions. Too much tension creates weak points that tear easily, while insufficient tension results in wrinkled membranes that reduce light transmission and weather resistance. Installation of both ice and bladder windows uses traditional sealing techniques that create weatherproof connections without modern caulks or sealants. The seals use combinations of moss, animal fat, and birch tar that remain flexible in extreme cold while providing complete weather protection. These natural sealants actually improve with age, becoming more effective as they cure and settle into the joint surfaces. The window systems include interior shutters made from wooden panels that can be closed during the most severe weather, providing additional insulation when maximum thermal protection is needed. These shutters are fitted with traditional hardware that operates reliably in extreme cold, using wooden pins and leather hinges that don't become brittle or fail like metal components would. Step 6. Interior climate control and living systems. The balaghan's interior represents a carefully engineered living environment that maintains not just survivable temperatures, but comfortable conditions that support family life, food preparation, and essential winter activities. The interior systems manage temperature, humidity, air quality, and space utilization with sophistication that rivals modern climate control systems. Interior space organization follows traditional patterns that optimize both thermal efficiency and family function. The area closest to the Kaunas serves as the primary living space where families gather for meals, conversation, and essential winter activities. This zone maintains the highest temperatures, typically 65–70 degrees Celsius, providing a comfortable environment for detailed work and social activities. Sleeping areas are positioned to take advantage of the Kaunas heat while providing privacy and comfort for family members. Traditional sleeping platforms, raised 18 to 24 inches above the floor, take advantage of warm air stratification while providing storage space beneath for essential supplies and equipment. The platforms are constructed using traditional joinery that creates strong, stable sleeping surfaces without metal fasteners that could conduct heat away from the sleeping area. The platforms also serve as seating with traditional cushions using reindeer hides, bird down, and woven grass for insulation and comfort. Humidity control represents a critical aspect of interior climate management, as excessive moisture can create condensation that destroys insulation effectiveness, while insufficient humidity creates health problems and increases fire risk. The balaghan's design includes passive humidity control systems that maintain optimal moisture levels without mechanical systems or constant attention. The Kaunas combustion process provides controlled humidity through the water vapor produced during wood combustion, while the clay construction materials absorb and release moisture to buffer humidity swings. The interior walls, finished with clay-based plasters, act as humidity regulators that absorb excess moisture during cooking and bathing activities while releasing it during dry periods. Ventilation systems provide essential air exchange while minimizing heat loss through carefully designed openings that create controlled airflow patterns. Small openings near the roof peak allow hot, humid air to escape while drawing fresh air through lower openings that are warmed by the Kaunas before entering the living space. This creates a natural circulation pattern that maintains air quality while preserving thermal efficiency. Food storage areas use temperature zones, cooler areas for refrigeration, warmer zones for preparation. Traditional birch bark containers provide pest-proof storage while regulating humidity. The interior lighting system uses the Kaunas fire as the primary light source, supplemented by traditional oil lamps that burn fish oil or animal fat. These lamps are positioned to provide task lighting while contributing to the interior's heating system. The lamp design uses traditional wicks made from moss or cattail down that burn cleanly while providing steady, reliable light throughout the long winter nights. Work areas for tool maintenance and craft production use natural light while staying close to the Kaunas for warmth. Traditional storage systems keep materials organized. Step 7. Maintenance systems and seasonal adaptations. The balaghan's longevity depends on sophisticated maintenance systems that address the unique challenges of extreme cold, permafrost movement, and seasonal weather variations. These aren't simple repair techniques. They're integrated maintenance philosophies that keep structures functional for decades while adapting to changing conditions and family needs. Seasonal maintenance cycles follow traditional calendars that align maintenance activities with optimal weather conditions and material availability. Spring maintenance, conducted during the brief thaw period, focuses on structural inspection and repair of winter damage. This includes checking foundation stability, repairing insulation damage, and replacing worn components before the next winter season. The Saman insulation system requires annual maintenance to address cracking, settling, and weather damage that occurs during the winter season. Maintenance techniques use fresh cement mixtures applied to damaged areas, with the repair material formulated to match the existing insulation's thermal and structural properties. Experienced builders can assess insulation condition by observing interior temperature patterns and identifying areas where thermal performance has degraded. Structural maintenance addresses the effects of permafrost movement, thermal expansion, and settling that occur throughout the annual freeze-thaw cycle. Traditional techniques allow for controlled movement that prevents structural damage while maintaining the building's integrity. Joints are designed to accommodate movement while maintaining weather seals, using traditional materials that remain flexible in extreme cold. The Kamalek requires regular maintenance to ensure safe, efficient operation throughout the winter season. Chimney cleaning removes creosote buildup that could cause dangerous fires, while combustion chamber maintenance ensures optimal burning efficiency. Traditional cleaning tools and techniques address these maintenance needs using materials and methods available in the Siberian environment. Roof maintenance addresses snow load management and ice dam prevention that could damage the structure or create dangerous conditions. Traditional techniques include controlled snow removal that maintains insulation benefits while preventing overloading, and ice management systems that prevent dangerous ice formations around the structure. Window system maintenance includes ice panel replacement and bladder membrane repair that keeps the light and ventilation systems functional throughout the winter. Traditional techniques create replacement panels and repair damaged membranes using materials and methods that restore full functionality without compromising thermal performance. Emergency repairs use reserved materials and quick implementation techniques for sudden damage. Seasonal adaptations optimize performance year-round, while traditional knowledge transfer ensures skills pass between generations through hands-on training. Modern studies of well-maintained balaghans show structures remaining functional for 50 to 80 years, with some examples exceeding 100 years of continuous use. This longevity results from maintenance systems that address problems before they become critical while adapting the structures to changing conditions and needs. Contemporary permafrost construction projects study these traditional maintenance approaches to develop modern techniques that achieve similar longevity and reliability. In 1962, Soviet engineers studying traditional Yakut construction documented a balaghan that had housed 5 generations of the same family, maintaining interior temperatures above freezing through winters that killed thousands of unprepared settlers. The structure's maintenance records, kept by the family for over 80 years, showed systematic care that preserved not just the building, but the knowledge systems that made such remarkable longevity possible. Let me know in the comments which aspect of Yakut shelter construction impressed you most. Was it the sophisticated Kama insulation system or the ingenious Kamanek heating design that maintains 55 degrees Fahrenheit in minus 96 degrees Fahrenheit conditions? See you in the next episode.